Mine is a practical FYP project done out of the Electronic and Computer Engineering Department in UL. So we'll be going through these sections in it, but basically it's about, there's a fleet of submersible ROVs in the Centre for Robotics and Intelligence Systems. And we were looking at ways to develop new tools for these submersible ROV systems to use. So a lot of these platforms, they're used for inspection in the likes of oil and gas or in marine science missions. And they have a lot of sensors on board, but the cornerstone of those is the camera. And nearly every one of them, it's the most basic sensor they use. So we were looking at using the camera to introduce the ability for the pilot, whether that be a control system or a human pilot, to define an object and then track that object in the field of view. And in particular, it needs to be viable in low light conditions. So we were using edge detection and template matching. And then I won't go too into detail here, but the basics of edge detection is if you look at the colors of the pixels in an image, in the bottom left there, you can see a line profile. So that steep slope there is the area where there's a rapid change in the light levels. And the top right shows a spike where that rapid change occurs. So we can use that spike to isolate levels of rapid change, and that's what we call an edge in a vision system. And there's a couple of formula there. So using those formulas, we can get a strength and a direction, and we can apply that all across the image and build up a map of these things we call gradients. And this is just an example of a specific edge detector, the Canny edge detector. These are the 5 steps to go through. So you start with your original image, you smooth it out. When you apply your edge detector, you start with this very, very noisy image. And through a process of cleaning it up and filtering it, we get that final, very clean line edge that we can use. And that's a very useful one in computer vision. So, and again, there's a bit more formula here, but the basics of this is when we take a particular image, apply our edge detector, we get a set of equations that describe it. And if we compare that across a target image, we can look for a correlation score. And on the bottom right, you should be able to see a very high spike. That's the area of best match. So that's how we take an image, compare it to a target image and say, well, when we place it here, this is our best match. And that kind of forms the basis for tracking an object and detecting an object. And a lot of machine learning can use this technique or some other techniques, but we avoided machine learning here because you need big data sets, you need time to train, and that's a luxury you don't have when you're out in the field. So that's why we opted for this particular method. So again, this is just a brief section on how we can use the location of this target to control the ROV. So you can use relative velocity, and it's a method of calculating how your target is moving relative to you. So if I treat myself as stationary and I see the target moving towards the left of the screen, I must move left in order to compensate and keep that target centered. Or you can simply track it for informational purposes. So to develop the solution to the problem, we needed to operate in low visibility conditions, and I went for a state machine model, which is it's well known in engineering, at least, especially computer and electronic engineering, where it's a system where you have a lot of different states, and there's logic that moves you from one state to another. So on the right there, we have a default loop where we get an image, we apply some image processing, we overlay any information we need to, and we show it back to the front panel to the user. And then if there's a button pressed, you can move into a different loop, or some other button will move you into the snapshot loop, for example, where you capture an image. And on the left is their secondary default loop, where It's the same as the first, only we're applying the matching functionality in that state. So this was my logic diagram, if you like, for the program. And after that was to build it. So Labview was the development environment. It's a type of visual coding. So instead of lines of text, you have symbols that represent logic. The individual states were created, the core functionality was created, and because of the state machine, you can develop it in pieces, and you can test this piece, does it work? Test that piece, does it work? Put them together, does it work? And then the last thing was to build this front panel that the user can interact with and to test. So I think I have a short video here just showing clear, like perfect conditions in nice clean water, and then the low visibility. So I'll just talk you through. So this is taking a snapshot. You target your object. In this case, it was a marker, and that's the starting image. And then you set your correlation score. You press the magic match button, and there you go. So it's when you have big changes in lighting, sometimes it does drop off. But whether you're moving around, changing in scale, the targeting was pretty consistent. And towards the bottom right there, you have a set of coordinates. This is just an occlusion test, so even if you cover part of the marker up to a point, it'll still detect it. And this is our low visibility, so it's quite hard to see it without adjusting brightness and contrast. But you'll see now that like you can target this pretty blurry object, and the program still tracks it pretty well. Like, so you've got your left and right, and through changes in scale, so the marker becoming larger, it's about 50% changes in scale are tolerated. Rotation left and right, and rotation on the vertical axis as well. So I was pretty happy with these results. This is more akin to realistic conditions. Like the clear water was just a proof of concept. So that was it. There was a lot of research done into the best, mathematical techniques for implementing this. And again, because of the constraints of you might come across an object that you've never seen before, and there's no data set for that. So that's why we went with this template pattern matching. So yeah, that's about it. I'd like to thank my supervisors, and if there's any questions, I'll take them now. So thank you.
That's great. Thanks very much, Luke. And I'll